Percent composition. Percentages are very useful, and we actually use them in real life, so it's useful to understand what percent means. So here's a little example from my family's now long ago history. James, when he was in kindergarten, his class had 15 boys and 5 girls. And I found out actually at the end of the year that at the beginning of the year, only half of them spoke English, which doesn't look like a good setup for a successful kindergarten year, right? But he had a fabulous year. It was just a great year. It was a great class with 15 boys and 5 girls. That's just kind of crazy. But that was a long time ago because James just turned 21, so that was a while ago. But anyway, it makes a nice example. What percentage of the class were boys? 75. We can kind of do that in our heads. But what does percent mean? One way to define percent is it's the part that you're looking at divided by the whole thing, and then we multiply by 100 to get a percentage. Because if all the children were boys, then the part would equal the whole, and we would end up with 100%, meaning it's all just one kind. But in this case, we had 15 boys and 5 girls. So the percent is going to equal the part we're interested in, which is the 15 boys, divided by the whole class. Well, the whole class was 15 plus 5, which was 20 students. So 15 out of 20. And then we multiply by 100. When you do that on your calculator, you get 75%. A percentage applies no matter what size the sample is. So if we said, okay, here's an entire school, and 75% of the children are boys, then we could figure out how many are boys if we knew the number of children. But percentages don't change based on the size of the sample. So we use percentages when we're talking about the composition of compounds as well. So when we talk about a mass percent of an element in a compound, here, instead of looking at the number of boys, we're looking at the mass of a particular element in the compound. And then we're going to divide by the mass of the whole compound. So again, it's the part over the whole times 100. So let's find the percent of iron in iron 3 oxide. The formula is Fe2O3. So the percent of iron by mass is going to equal the grams of iron, the mass of the part, divided by the grams of the whole thing, the Fe2O3, and then multiplied by 100. That's really ugly right there. Does the problem give us the mass of iron or the mass of the iron 3 oxide? It doesn't. How do we do this then? Well, what we do is we just pick a size. We could pick 100 grams of iron 3 oxide. We could pick 1 iron 3 oxide molecule. We can choose any size sample that we want, just like with the cars and the bicycles and stuff. The number of wheels per thing. Yes?
Can you apply that with molarity as well? Percentage of a mole, since you're talking about quantity?
Molarity is moles per liter. And so that's a different sort of a relationship than percent. It's related but different. Well, what we're going to do is we're just going to choose something that makes our lives easy. Let's just say we had 1 mole. Then it would be really easy to calculate the mass of the whole compound. You just say, well, So we'll say, let's assume, of course you know what assuming does, but let's assume 1 mole of Fe2O3. What's the mass of 1 mole? The molar mass, right? So we can calculate the mass of the Fe2O3 by calculating its molar mass. So there's 2 iron atoms, 55.85, and there's 3 oxygens, and each of those is 16. And we find out 2 times 55.85 plus 3 times 16 equals 159.7 grams per mole. Or we can say 159.7 grams equals 1 mole. So that is the mass of the compound, 159.7 grams. What's the mass of iron in that amount of iron oxide? It's this part right here. How did we figure out the mass of the compound? We took the mass of the iron and added the mass of the oxygen. And we showed our work, and so up here, this is the mass of the iron. Because in 1 mole of this, there are 2 moles of iron. So we've got 2 times 55.85, 2 times 55.85. That's the mass of the iron. That goes on the top, 117. No, I was right, 111.7 grams. So we're going to take 111.7 and we're going to divide by 159.7 and multiply by 100. And I used 4 significant figures in my molar masses, and so I'm going to use 4 significant figures in my percentage here, 69.94%. Is that a reasonable answer? What if I got 6,000%? That be reasonable? No, because that would be like saying in a class of 20 kindergarten children, 30 of them are boys. Right? How could you have more boys than you have children, right? When we do percentages like this, you can't get more than 100%. 100% is all of it, right? There are some situations where percentages can be greater than 100, but not in a percent composition. So your percent should be between 0 and 100. If you get a negative in there, then you've really got a problem. There are no negative masses. Any questions? Part over the whole times 100. And so if we're calculating a percent composition, you just have to choose a sample size. And you could choose anything, but choosing 1 mole just makes it so much easier. So we say, well, let's say we have 1 mole. What's the mass of a mole of the compound? And then in that compound, what's the mass of the element that I'm interested in? Take the mass of the element divided by the mass of the whole compound, multiply by 100. And the unit on this is percent, because the grams canceled out, didn't they? We had grams divided by grams, and they canceled out. Percentages really don't have a unit. Let's do another one. Morphine, which is derived from opium plants, has the potential for use and abuse. Its formula is C17H19NO3. What percent by mass is the carbon in this compound? Okay, that first sentence we don't really need. That's just kind of interesting background information. We're trying to find the percentage of carbon. What percent by mass is the carbon? So percent carbon, that's going to equal the mass of carbon divided by the mass of morphine, divided by the grams of C17, H19, and O3. And then we're going to multiply that by 100 to get a percentage. So how do we figure out what those masses are? We're just going to assume a mole. Say 1 mole, we'll find the mass of 1 mole of morphine, and then we'll find the mass of carbon in 1 mole of morphine. So there are 17 carbon atoms, and each, or 17 moles of carbon atoms, each mole weighs 12.01 grams. And there are 19 moles of hydrogen, and that's 1.008. And there's 1 mole of nitrogen, 14.01, and 3 moles of oxygen. So this is probably going to be kind of a big number, huh? 17 times 12.01 plus 19 times 1.008 plus 14.01 plus 3 times 16. 285.3. That's grams is equal to 1 mole. That's the mass of morphine. The mass of 1 mole of morphine. So that goes in the denominator, 285.3 grams. That's going to be times 100, and now we need to know the mass of carbon. That's this part over here. So we'll find that, and that goes up. That's not what I wanted to do. Oh, look at that. Didn't know I could do that. Didn't want to do that. That's what I wanted to do. 17 times 12.01. 204.17. That's the mass of the carbon. So I'm going to take that, I'm going to divide by 285.3. That gives me 0.7156, blah, blah, blah. Multiply by 100. And I get 71.56%. So this one was multiple choice. Which is the best answer? Letter D. They just used a different number of significant figures. Any questions? We'll finish this on Monday.